The second method that we're going to learn for solving systems is using the substitution method. So basically the substitution method is going to require us to solve linear equations for one variable. When we have the choice of two equations, we can pick either the first or second to solve for that variable. Then we're going to substitute it into the second equation so that we can solve for the other variable. So we're going to work on finding these substitution equations. We're going to work on solving them if there's fractions involved. And then we're also going to talk about how we can identify whether something is an inconsistent or dependent system of equations using the substitution method. So when solving the systems of equations by graphing, it's often difficult to determine the exact coordinates. For instance, if the solution was 1/16, -3/5, there's no real way that you'd be able to tell exactly where it is if you were trying to do it by hand. Whereas with the substitution method, we could find an exact answer like this. So this is the example that we're going to look at. Basically, if I have y equals 3x minus 2 and 2x plus y equals 8 is my system, I can see that this first equation is already solved for y. What the substitution method is going to ask us to do is take what we've solved for y and plug it in wherever we see a y in the second equation. I'm going to ask you to always remember to put parentheses around it, because a lot of times we're going to have a number in front of the y or a sign in front of the y. So this time there's an understood 1 there, but if it said, for instance, -3y, we put 3x minus 2 in parentheses where the y is, and that would remind us to multiply by what's on the outside. So a lot of the mistakes that come in this method come from not properly doing the distributive property. Remember that if you have a number outside of parentheses and then two terms inside the parentheses, what's happening outside gets multiplied by each of the two things inside. That said, in this particular example, we don't need to worry about that because we're just plugging in for one single y. So when we plug it in for that one single y, we're taking what we know y to be, 3x minus 2, putting it down here where we see the y in the second equation. Now the second equation becomes 2x plus 3x minus 2 equals 8. We've gone from an equation with two variables to an equation with one variable. An equation with one variable and just numbers, I can solve for that variable and find exactly what x equals. The way that I'm going to do it is I'm going to start by combining like terms. So I'm going to take 2x and 3x. They both have the single power of x, so they are like terms. 2 plus 3 gives me a total of 5x. I now have to deal with this -2. To move it to the other side, I'm going to add 2 to each side. That's how I get to 5x equals 10. Now I want just 1x. So what's currently happening is x is being multiplied by 5. To undo multiplication, I'm going to do division. So I'm going to divide each side by 5. That's how I get to my answer of x equals 2. That's half the answer. Whenever we solve a system, we want to get the ordered pair x, y that's the solution to the systems of equation. So in this case, x equals 2 is not both pairs, both parts of the ordered pair. It's only the x value. To solve for the y value, we want to take that 2 and plug it back in to the equation that we have solved for y. Specifically, y equals 3x minus 2. So if we put that 2 in where we see an x, we get y equals 3 times 2 minus 2, which becomes 6 minus 2, which becomes 4. We now know that the system of equations can be solved with an x value of 2 and a y value of 4. We can always check the same way that we checked in the past by looking at the two original equations, saying what happens if we put this x and y in. If we put in 4 for y, 2 for x in the first equation, we get 4 equals 4, which is true. If we put in 2 for x, 4 for y in the second equation, we get 8 equals 8, which is true. Since we get two true statements there, we know that yes, this is a solution to the systems of equation. If we graph them, this would be the point that they intersect at, but the goal here is to not have to graph them. So the graphical method was the first way that we learned it. Now we're learning it in a way that we can do all the calculations by hand, solve for the variables, and know that this is the solution to the equation without having to worry about putting it on a graph. So step by step, what we're going to do, the first thing we're going to do is solve one of the equations for either x or y. I know we've gotten really used to solving for y in here, but when we're doing the substitution method, there might be times where it's easier to solve for x. So always look for an equation that's already solved for a variable when you're doing this. If you have something that's y equals or x equals, start there and plug that in for the other variable. But a lot of times you'll get something that isn't solved for either one. Don't feel like you always have to choose y. Choose whichever of the two variables will be easier and give you less fractions, basically. Once you've solved for either x or y, then you substitute the expression for x or y obtained in step 1 into the other equation. That way, the equation that you're substituting into goes from having two variables to only having one variable. Once it's down to one variable, we can solve it for what value that variable takes on. Just like previously when we solved and got an x value of x equals 2, when we solve and get the first of the two coordinates, we have to plug it back in to get the second of the two coordinates. So step 4 is that we substitute back, step 3 is that we substitute back into step 2 and find what the remaining variable is. Step 4, which again you don't necessarily have to do, but it's good practice, is just check that yes, that does solve both equations. So to find the substitution equation, we have to solve for one of the variables. If possible, we really would like a coefficient of 1 or -1 to avoid working with fractions. So let's say we have 2x plus y equals -5 and 3x plus 5y equals -4. I technically could solve any of these equations for any of the variables, but if I'm looking for the one that's not going to give me fractions, this y is all by itself already. If I move this 2x to this side, I'll get a whole y that I can plug in here into the second equation for y. So the first thing that we're going to do is move the 2x to the right. That's how we get y equals -5 minus 2x, or really I'd prefer you to write it as -2x minus 5, but really they're the same thing. We substitute it in wherever we see a y in the first or in the second equation. So now remember that when we're putting in this -5 minus 2x, all of it has to be multiplied by this 5. It's not just this 5 times the -5, it's this 5 times the -5, and then this 5 times the -2x. That's why when I substitute in, I like to put parentheses around what's coming in to make sure I remember to do the distributive property. So here's the parentheses. The parentheses remind me that I'm doing 5 times -5 to get this -25, and then I'm also doing 5 times -2x to get this -10x. I now look on the left side and say I do have two like terms, specifically this 3x and this -10x that can be combined. 3x minus 10x gives me -7x. I now need to take this -25 to the opposite side. To do that, I'm going to add 25 to each side. When I add 25 to the left, it gets rid of it. When I add 25 to -4, I get +21. If I now divide each side by -7, I'll get what just 1x equals. 21 divided by -7 gives me -3. Since I now have the answer for x, I can plug it back in to find what the answer is for y. If I plug in the -3 that I got for x into the equation that's already solved for y, it becomes -5 minus 2 times -3. -5 minus 2 times -3 becomes -5 plus 6, which is just y equals 1. I now have both the x and y value for my system of equations. X equals -3, y equals +1. So I can write that as an ordered pair, -3, +1. I can go back and check if I want and plug it in to double check that yes, this does solve both equations. It does in this case. Sometimes you'll see things that aren't written in x and y, so sometimes they'll be written in a and b. Definitely, if you guys are going to go on and do chemistry, you're going to have to learn how to work with variables that aren't always labeled as x and y, so don't get thrown off by that. Basically, if you have two variables, you do all the same steps here. You solve for one of the letters, plug in for that letter in the other equation, which gets it down to one variable that you solve for. Use it to find the first variable, which will then give you a solution point. That solution point should go in alphabetical order. So X, Y is in alphabetical order, A, B would be in alphabetical order. You could have problems that gave you answers C, D. Sometimes for scientific reasons, you might want to have something that's like a time variable and a temperature variable, where maybe time comes first and temperature comes second, even though that's not alphabetical. But for this class, if you're given letters, they're mostly letters without context for these, put them in alphabetical order as ordered pairs. So if these contain fractions, usually what you want to do is get rid of the fractions to start. I'm trying not to give you too many like these, so don't get too worried if you absolutely hate fractions. Do be worried that the fourth unit in the course deals with them, and you will have to worry about them in the future. But for this unit, I'm hoping there's not as many that trip you up on fractions. Maybe there'll be one or two per section. So, way that I deal with it, I just want to get rid of all these fractions in this first equation. What I would do is I would multiply the entire equation by 4. If I multiplied the whole thing by 4, multiplying this term by 4 would make it 2x, multiplying this term by 4 would just make it y, and multiplying this term by 4 would just make it -1, which would mean I no longer have to worry about fractions being in the equation. So, here we see the least common denominator is 4. It's what we choose to multiply by. That's how we turn x over 2 plus y over 4 equals -1/4 into 2x plus y equals -1. When we look at this second equation, we can move things around. We can take this -x to this side by adding x to each side. If we add x to each side, this becomes a positive 3x. We can move this plus y by subtracting y from each side. -y minus y gives me -2y. So you can see they're doing these moves over here. They're subtracting y to get rid of that. They're adding x to get rid of that. They end up with just 2 on the right, and then they get 3x from this x plus that 2x, and -2y from that -y and that -y combined. So here I have two equations that are much easier to work with. The substitution method, cleaned them up a little, getting rid of the fractions by multiplying by the common denominator, getting rid of the common terms by taking all the letters to the left and the numbers to the right. Solve the system. We can see that y would be the easiest thing to get by itself. To get that y by itself, I'm going to move this 2x by saying subtract 2x from each side. Now I have y equals -1 minus 2x. I can put that in where I see a y in the second equation. Where I plug that in, I need to remember to put in parentheses so that I'm sure that whatever's outside gets multiplied by each part of the parentheses. Understand that this negative matters. That negative that goes with the 2 gets multiplied by the -1. That negative that goes with the 2 also gets multiplied by that -2x. So it becomes +2 and +4x. -2 times -1 gave me that +2. -2 times -2x gave me that +4x. If I now combine the left side, I get 4x plus 3x gives me 7x. Since this 2 can't be combined with x's, I can move it to this side by subtracting 2 from each side. That gives me 7x equals 0. If I divide both sides by 7, I get to just x equals 0. Since I know x equals 0, I can plug it in to my substitution equation. -1 minus 2 times 0 just gives me -1. So I now have the solution point, x equals 0, y equals -1. 0, -1 as an ordered pair is the correct solution. I could plug it into each equation to show that yes, it works in each of them. When we're talking about inconsistent systems and dependent systems, basically what's going to end up happening is when I do my substitution method, both variables will disappear. So it'll be something where when I plug in for my solved y or x, it'll get rid of both y and x in the new equation. because both y's and x's will be gone, it'll either end up being a true statement or a false statement. When I say a true statement or a false statement, it'll either end up saying something like 4 equals 4, true, or it'll end up saying something like 2 equals 4, false. If it's a true statement like 4 equals 4, then you say that it's a dependent system. Basically, you had the same line. If it's a false statement like 2 equals 4, then you say it's an inconsistent system. Basically, you had 2 lines with the same slope, but different intercepts. So, we're going to see how this plays out. Basically, we're going to multiply the first equation by 100 to get rid of all those decimals, and we're going to do the distributive property and then take all the letters to the same side in the second equation. So when we multiply the first equation by 100, we get x equals 12 minus 4y. When we distribute the second equation, we're putting in this 12 minus 4y wherever we see an x. So that's why it's been replaced. X became 12 minus 4y because this was solved for x. Now we have 2 times 12, which gives me 24. 2 times negative 4y, which gives me negative 8y. On the other side, we have 4 times 3, which gives me 12. 4 times negative 2y, which gives me negative 8y. As you can see, if I try and move all the y's to the same side, what I'll end up doing is adding 8y to each side, which means both of them will disappear. Therefore, we're only left with numbers. At this stage, when we only have numbers, we check if it's a true statement or a false statement. 24 does not equal to 12, so here we have a false statement. Since we have a false statement, we say that it's an inconsistent system with no solution. So this indicates that the system is inconsistent. What they want you to do in Cengage is write capital letters inconsistent. If we had graphed these lines, this is what they would look like. 2 parallel lines that never touch, which again is why they are inconsistent.